Most people have absolutely no idea that there are airplanes flying in the sky right now carrying hundreds of thousands of 3D printed parts. Not prototypes, not demo parts, not test coupons sitting in a lab somewhere. Real, certified, flight-ready production parts made using industrial additive manufacturing and high-temperature 3D printing. If you've flown in the past 5 years, there's a very high probability that you were sitting on an aircraft that had hundreds, if not thousands or even tens of thousands of 3D printed parts installed on it. And most passengers, and honestly even a lot of engineers, have no idea that this is already happening. People still think I'm joking when I say this. They're like, wait, what do you mean tons of the plane is 3D printed? And no, we're not talking about printing the wings or the fuselage, but a massive portion of the functional interior and system components are absolutely being produced with 3D printing today. This is a quiet engineering revolution that's been happening in the background for years. And one of the clearest examples of this is what Airbus has been doing with the high-performance polymer 3D printing, especially using Ultem 9085 or polyether imide 9085. And this is exactly the category of work that we design systems like the 22IDEX for. Real high-temperature polymer printing, real repeatability, real production workflows, and not hobby machines. Most people's mental model of 3D printing is still stuck about 10 or 15 years in the past. They think of prototyping, maker projects, fit checks, toys and trinkets, and visual models, things like that. And to be fair, that used to be absolutely true. Consumer and hobby machines have exploded into the mainstream, and that's what's dominated the conversation for the last decade or so. But quietly, in industrial environments, additive manufacturing has been maturing for a long time. Process control has gotten better, materials have gotten better, machine stability has gotten better, repeatability has gotten better. And the strongest validation you can possibly get for any manufacturing technology is aerospace adoption. Aerospace does not adopt technology casually. It doesn't chase trends, and it absolutely does not tolerate variability. So when aerospace adopts something, especially at a production scale, it means the technology has crossed a very serious credibility threshold. Again, this is not hype adoption. This is conservative, validated, long-term deployment. So let's talk about what Airbus is actually doing. Airbus is not experimenting with 3D printed parts. They are operating sustained production workflows where additive is simply part of how parts get made. These parts are already flying across multiple aircraft platforms. Production volumes are significant and meaningful, and they've been repeating this year over year. Now, this isn't just one lab running like a pilot program. No pun intended. It's not one individual factory that they converted to be for 3D printing and they're trying something new and flashy. It's not one prototype buried somewhere in a test fleet of airplanes. Once parts become certified and embedded into an aircraft production ecosystem, it's almost not even reversible. At that point, additive has become part of the infrastructure, and that is a massive shift. Let's get tangible for a moment. When people hear 3D printed parts on airplanes, their imagination goes straight to the wings or the structural frames or stuff like that, big stuff, right? The real wins show up in functional interior and system components like cabin interior components, tray tables, panels, interior structures, brackets and housings, ducting, airflow management, HVAC systems, structural interior parts, or the service and replacement parts. Now, these kinds of things are perfect for 3D printing because the geometry can be very complex. Production volumes are usually low to medium. Weight matters a lot. Parts can evolve over time, and spare parts logistics are painful with traditional manufacturing. Even a part that might take days or weeks to machine can often be printed in hours. You don't need to tool up for a massive volume of production when the fleet size is pretty limited. If a part needs a design improvement after 6 months in service, you can iterate it without scrapping thousands of molded spare parts sitting on a shelf somewhere in a warehouse. And instead of warehousing spare parts for decades, you can digitize the inventory and print them as needed. And this is exactly where 3D printing creates immediate real-world value. And practically speaking, this is the sweet spot for machines like our 22IDEX. Complex geometry, engineering thermoplastics, low to mid-volume production parts, fast iteration, and real uptime requirements. When you look across aerospace additive manufacturing, right, one material keeps showing up over and over again, and that is Ultem 9085, or polyether imide grade 9085. It's a high-performance aerospace thermoplastic that's really well known for its flame, smoke, and toxicity performance with a UL94 V0 FST rating, a very strong strength-to-weight ratio, great mechanical properties, and stable processing, especially in industrial FDM environments. It's also a high-temp thermoplastic that can survive demanding operations and environments while remaining printable at scale. One of the biggest reasons Ultem 9085 became so widely adopted is that it's been actually around quite a long time in industrial 3D printing. Stratasys was pushing this material early back in the 2000s, and it developed a long track record in aerospace and transportation applications. By the late 2000s, it was already gaining traction for flight-adjacent environments for its durability, its heat resistance, and its mechanical performance. So this isn't a brand new experimental polymer. It's mature, it's proven, it's standardized. And that is a big deal in every regulated industry. If you care about aerospace 3D printing materials, high-temp polymers, FST-compliant thermoplastics, or production additive manufacturing, then Ultem 9085 sits right at the center of that whole conversation. Aerospace is conservative by necessity, right? If something fails, people can get seriously hurt or even potentially die. So certification barriers are extremely high. Safety dominates every decision. Traceability matters, repeatability matters even more. If a process can't be controlled, it doesn't get adopted. Aerospace rarely moves quickly, but once something is validated, it often stays in production for decades. So if Ultem 9085 and industrial FDM 3D printing are accepted in aerospace environments, then they're effectively proven for almost every other industry. Defense looks at aerospace. Transportation looks at aerospace. Energy, oil and gas, they look at aerospace. Industrial equipment manufacturers look at aerospace. Aerospace is essentially the global technology filter. Airbus didn't adopt 3D printing because it was a trend and it was the hot thing. They adopted it because it was solving real operational problems. Additive manufacturing enables much shorter lead times, less dependency on tooling and machine shops, opportunities for weight reduction, faster design iteration, better service and spare parts availability through having a digital inventory. Instead of being locked into massive upfront tooling commitments and long-term supply chains, they gain a lot of flexibility and responsiveness. Now, we'll go much deeper into the economics and certification side in future videos because that's where things get really, really interesting. So make sure you're subscribed and you catch those. The big takeaway is this. High-performance polymer additive manufacturing is no longer just emerging, it's established. Aerospace adoption validates that. And what works in aerospace inevitably migrates into defense, transportation, energy, industrial equipment, oil and gas, medical, all industries that we've been serving for a decade as Vision Minor. And eventually, even more broad commercial and consumer applications will be in its wheelhouse. At Vision Minor, this is exactly the world that we've been operating in for nearly a decade. We specifically do not focus on hobby machines. We focus on real engineering systems, high-temperature thermoplastics, production stability, maintainability, process reliability. The Vision Minor 22 IDEX was built specifically for this class of work. Engineering plastics, controlled thermal environments, long-duration prints, and repeatable production workflows that businesses can actually rely on. We spend a lot of time helping customers evaluate whether additive actually makes sense for their application, and sometimes even talking people out of machines if it's not the right fit or the timing. Long-term success in this space isn't about selling boxes or chasing volume numbers. It's about building reliable manufacturing workflows, strong customer relationships, and technology that actually works in production. That's how you build trust. Additive manufacturing didn't win aerospace through hype. It won it through reliability, discipline, and frankly, a lot of boring excellence and failures over many, many years. Ultem 9085 represents that maturity curve extremely well. If you want more deep dives into aerospace 3D printing, high temperature polymers, real industrial workflows, then subscribe and stay tuned. And if you're exploring how additive might fit into your business, printers, materials, 3D scanning, or process integration, we're always happy to help. Anyway, thank you so much for watching the video. Leave a comment down below. Have a positive rest of your day. I'll see you on the next.